let's move to the final talk. And this is going to be given by Juan, whom you already know. Juan, are you there?
Yes, I am. Okay,
great. As you know, Juan is a senior researcher working with me, and he is, well, since you're taking the course, you know, and he's been working a lot on processing in memory recently, and he's going to talk about the UPMEM processing in memory architecture that we briefly mentioned earlier in the course. This is really the first, let's say, commercially destined processing in memory architecture that has been implemented in real hardware. And we'll see if it's going to be successful, but it's important to examine its architecture, its programming model, where it benefits, where it doesn't benefit, so that we can potentially improve things going into the future. So Juan, go ahead.
Yeah, thank you, Honor, for the introduction. I'm going to give this talk. The title is Understanding a Modern Processing in Memory Architecture. And as Professor Mudlu said, we are going to talk about the new UPMEM PIM architecture. Let's start with a summary of this work in order to state what are the goals of this presentation and the goals of the research work that we are doing. All of you are already familiar with the processing in memory paradigm, which is the way that we are pushing for in order to be able to tackle the data movement bottleneck. And from Professor Mudlu's lectures, you are already familiar with the research that many people are doing and our group is also doing. And one of the things that you must have noticed is that there were not yet real world devices. This is not really a problem for the research that we do, because we use other tools like simulators, for example. But it's also true that it does not allow us to define what are clear baselines in order to be able to improve the existing architectures and make our proposals. And this is what we can, one of the things that we can have with the fact that we have now a real world and publicly available processing in memory architecture. UPMEM is a French company that has designed and fabricated the first publicly available real-world processing in memory architecture. And as you will see in this presentation, it is composed of DDR4 chips that embed in order multi-threaded cores, that are called DRAM processing units or DPUs. Our goals in this presentation are first to introduce the UPMEM architecture and the way that we work with it, which is programming it. And we will also start understanding the architecture and maybe even pointing out to some potential improvements for future research. This is the outline of the presentation. First of all, I will start giving an overview of the architecture and the system integration, and then we will start going into the details about how to program the architecture and what are the different components that take part of this architecture as well. And at the very end, I will briefly introduce the research work that we are doing. So let's start with the overview. You all have seen this slide before because Professor Mudlu showed it in the computation in memory lectures. This is here on the right-hand side. You can see a picture of some UPMEM DIMMs. These are essentially resemble conventional DRAM DIMMs and include a certain number of chips. Concretely, we have like 8 chips or 16 chips. And within each of these chips, what we have is a number of DRAM banks. And attached to each of the banks, we have these DRAM processing units or DPUs. This slide is from a presentation given by Fabrice Devaux, who is one of the inventors of the UPMEM architecture at Hot Chips 2019. There are some interesting values, numbers here on the table, but I would like to comment on these two here, which represent a comparison in terms of energy consumption for accessing data in a server with conventional DRAM or in a server with PIM DRAM, with UPMEM DRAM, the cost of accessing a 64-bit operand from the memory, moving the 64-bit operand from the memory to the DPU, to the DRAM core. So as you can see, there are like 20 times potential energy savings here. And this is what represents like one of the most interesting and important points of this architecture, the fact that we can improve performance and we can greatly improve the energy consumption by using processing in memory. Processing in memory is on all ideas. You know, Professor Mutlu already introduced this. This is, yes, for example, one of the preliminary papers back in 1970, a logic in memory computer by Harold Stone. And since then, there have been research in the 80s, the 90s, and more recently, including our group, many research groups in academia and industry are doing research in order to enable processing in memory on future computing systems. You can read a summary of many of these works in this summary paper published last year in the Micro Journal, and also this other one in the IBM Journal of Research and Development, which has like a more workload-driven perspective. UPMEM made it. UPMEM fabricated the first real-world processing in memory architecture, but of course that wasn't easy. They had to skip many hurdles on the road. And one of the important things, and one of the things that I want to make clear from the beginning, is that the main difficulty of embedding cores into the memory, and in this case into DRAM, are related to the fabrication process, the design process and the fabrication process. There is one key difference between embedding cores into a DRAM chip and doing it on a conventional ASIC process, and it's the fact that the number of metal layers that you can use is much smaller. So in the DRAM process, only 3 metal layers can be used for routing, while in conventional ASIC design, we can use 10 or more of these layers. And this imposes a lot of constraints in the design, makes the design quite difficult, and also forces to make some trade-offs, as you will see when we talk about the architecture itself. Yes, if you are curious, you can take a look at the patent that Fabrice Devaux and Jean-François Ra, as the inventors of this architecture, filed. I would like to read very briefly the abstract, because I think that it gives like a very good overview of what's the UPMEM system itself. The abstract says that the UPMEM system is a memory circuit which contains a memory array, probably with 1 or more memory banks, and a first processor. What is called here the first processor is what we just call the DRAM processing unit. It also talks about a control interface, which is the way for the first processor to receive commands from another processor, which is the central processor, or what we will call the host, which is usually a CPU, but could potentially be a GPU as well, or maybe other type of processor. And this central processor sends these commands for execution to the first processor, to the DPU. One important thing to keep into account here is that the memory banks are accessible to either the first processor or the central processor. So there is a way for the first processor to communicate to the central processor when some computation is completed, such that the central processor can access the banks and retrieve the results. And this takes us to what we call the accelerator model. Essentially, the accelerator model consists of seeing the UPMEM DIMMs as if they were a loosely coupled accelerator. where we need to explicitly move data between the main processor and the accelerator, which in this case is the UPMEM PIM architecture, and then explicitly launch the computation, the kernel, onto the UPMEM processors. This data movement that I just mentioned is going to happen between the main memory of the CPU and the memory, the DRAM memory in the UPMEM chips. So they coexist in the same system, conventional DIMMs and UPMEM DIMMs. And this model somehow resembles GPU computing. For example, this slide is from one of our GPU computing lectures and essentially explains how the process of loading computation to the GPU takes place. The first thing that needs to happen is that we transfer data, the input data from the CPU memory to the GPU memory. And then the CPU launches a kernel, launches the computation onto the GPU cores, which start operating on this input data, producing some result. And at some point, this result is transferred back to the CPU memory. So this is essentially what we are going to do as well with the UPMEM system. And it's actually something that is very well explained in this figure from the patent. In the very beginning, the system on chip, which is the CPU, loads data to be processed to the DRAM memory bank. Then this system on chip transmits the data processing command to the DRAM processor. So it says, okay, you can now start running the kernel. Then the processing takes place on the DPUs. And at some point, the computation will be completed and the memory bank becomes accessible by the SOC. If we take a look at the system organization, how are the different components organized and connected? We have in our system SoC, and then we have multiple DRAM chips. Within these DRAM chips, we have the memory arrays, and then we also have the processors. This is from the patent, and this is the system that we have access to and we are working with. It's a system with a host CPU. It's an Intel x86 processor, which is connected to 10 of these UPMEM DIMMs, each of them containing 8 pin chips. As I said, there is also conventional DRAM in the system as well. So this current setup has, as I said, 10 UPMEM DIMMs, which are, each of them constitutes a rank. And within each rank, we have 8 chips. And within each chip, we have 8 DRAM processing units. Each of them is attached to its own DRAM memory bank. These banks are called MRAM banks. MRAM meaning main RAM, which is, by the way, something to differentiate from the main memory of the system, which is a conventional DRAM connected to the CPU, but here it receives a similar name, MRAM. And in total, this setup has 640 DPUs and a total of 40 gigabytes of capacity. And as I said, this is connected to the x86 CPU with 2 memory controllers and several channels. And these 10 DIMMs plus the conventional DIMMs are attached to these memory controllers. This is not the most powerful system that you can plan for with UPMEM. It's gonna be possible. It's already possible to have like a much powerful configuration with 20 DIMMs of 16 chips each, because still in each of the chips we have 8 DPUs in total. This makes 2,560 DPUs in a system, and a total of 160 gigabytes. Okay, just to give you some food for thought from the beginning and some questions here. This is a loosely coupled accelerator that is connected to the CPU. Within the CPU, we will typically have more than one process running. And they can potentially, all of them can potentially access the UPMEM PIM system. So how is this access to the PIM system coordinated? Is it possible to share a DPU? Are there any security implications here? Well, what UPMEM tell us is that the DPUs cannot be shared across the multiple CPU processes. So that's in principle not necessary, because you are going to have many DPUs in the system. You have seen more than 2,000 DPUs in the system. So it is possible to partition them in a way that we give enough number of resources to each of the processes. And this has some advantages. Like, for example, there is no need for OS, and there are not many security implications, because in principle, you cannot have two processes running on the same processor. So they say, or in principle, we can expect that there are no side channels. But when I was preparing this slide, I was thinking about, okay, well, how could we still maybe try to perform some attacks here. And I thought about Rowhammer, right? It's obvious, because this system uses DRAM. So one question here, is it possible to perform Rowhammer bit flips in the UPMEM DIMMs, and could we somehow perform any attack at some point or plan for it? It's something to think about. Also, even though it's true that there is no way of having two processes at the same time on the same DPU, maybe there is a way of somehow attacking the previews of the next application that runs on the same DPU. Okay, let's start with the UPMEM PIM programming. We are going to start with a very simple example, vector addition, which is something that all of you know. It's like a very like a bread and butter of parallel programming. Imagine that you have two arrays, two vectors, A and B. And in vector addition, what we do is the element-wise addition of the elements of A and B, and we store the result on another array called C. So the way that we are going to distribute the computation in our UPMEM system is by partitioning the input arrays across the DPUs. So we divide the input arrays into as many chunks as DPUs we have in the system, for example, 4 DPUs in the system. And then inside each of the DPUs, we are going to partition the computation across the threads that run on the DPU. These software threads are called tasklets. So for example, here, we're going to assign this piece of data to tasklet 0, this one to tasklet 1, and we are going to do the same on the rest of the DPUs. Now, the next thing is, I have already been thinking about how do I want to parallelize my application on the UPMEM PIN system, but now one thing I have to do is to reserve the DPUs that I'm going to use. And for that, we need to create a DPU set. It's something very simple to do with an API called DPU alloc. Here, what we are saying is creating this DPU set with a certain number of DPUs. So, is it possible to allocate different DPU sets over the course of the program? That's one question that we can ask ourselves. And the answer is that yes, it's possible, right? So we can invoke this DPU alloc multiple times and just reserve the number of DPUs that we need at some point, right? And after we are done with them, we can deallocate them by using this DPU free. And actually, one example can be Needleman-Wunsch, which is an algorithm that you're already familiar with because of the talks in bioinformatics that you have had in this course. In Needleman-Wunsch, essentially, we have a matrix that we use to compare a reference and a read. And it's a waveform algorithm where we go diagonal by diagonal processing the data. The size of the diagonals, as you know, changes. So because of that, the number of processing elements, or in this case, the number of DPUs that we are going to use, it's going to change. And this is what we are going to do as we iterate on the algorithm. So based on what's the diagonal that we are processing, we are going to allocate a certain number of DPUs, in this case is number of blocks, because we divide the diagonal into multiple blocks, and we assign them to the DPUs. After we have allocated the DPUs, what we need to do is to explicitly load the program, the kernel, that is going to run on the UPMEM PIM system, or in multiple DPUs, or a DPU set in the UPMEM PIM system. And for that, we use this DPU load. We load a certain binary that is previously compiled in this file here, and we load it to the whole set. Now, one question is it possible to launch different kernels onto different DPUs? Yes, that's possible if we create like different DPU sets and we assign one kernel or one of these binaries to a different DPU set. And one interesting thing here is if we are using this in the same application for the same process, is that we can enable task level parallelism. So we can have two different DPU sets working on not only different data, but running the same program, but also computing completely different operations. And now the next thing is moving data between the main memory and the MRAM in the DPUs. And for that, we can use either serial transfers or parallel transfers. We are going to see the difference. Let's start with the serial transfers. We have two library calls here. One of them is DPU copy to, and the other one is DPU copy from. So as you can guess, copy to means that we are copying data to the DPU. Copy from means that we are reading from the DPUs to the main memory. And this is how these two library calls are used. So we need to define first of all, what's the address of the MRAM area that we want to use. In this case, we are using this constant here, which defines what's the start of the MRAM range that can be freely accessed by applications. And then we define an offset within the MRAM where we are going to start copying whatever we have in the main memory of the CPU. And then we have our pointer to the main memory here and the transfer size, which is the chunk that we are copying at once from the main memory in this case, because it's copied to from the main memory to the MRAM. And then we have the parallel transfers. In this case, we first need to prepare the transfer and then we push it. And pushing it is to the DPU or from the DPU. So it's semantically equivalent to the copy to or copy from. So here we have the pointer to main memory that we define in the preparation of the transfer. Then here we define the direction to or from the DPUs, the offset within MRAM, and the transfer size. Now the question is, where should we use parallel transfers and where can we use or should we use serial transfers? So this depends on the amount of data that we are transferring. So as you can see in the parallel transfer, in the push transfer, we have to define a transfer size, and this transfer size should be the same for all the DPUs. So whenever we have some sort of regular computation where we have a certain input data that we partition and assign part of this data, we partition the data evenly across the DPUs and we distribute to multiple DPUs, we can use parallel transfers. And the good thing is that these parallel transfers can be all executed at the same time. If that's not the case, then we will have to use serial transfers. And let me give you an example of that. For example, select, which is a database operator. In select, what we do is selecting or filtering a certain number of elements from an array, and those elements that fulfill some predicate. So in this particular example, in select, what we do is removing elements that fulfill a predicate, which in this case is true if it's even. So we are going to remove the even numbers from this input array. Imagine that we have 3 DPUs in our system, we partition the input array, and now the 3 DPUs are going to perform the select operation on the corresponding chunk. And as you can see, there are 2 odd numbers here, 2 odd numbers here, and 1 odd number here, right? And this is completely input dependent because it depends on what are the actual values on the input array. So the problem is that because we don't know in advance how many elements we will have to copy to the output array from each of the DPUs, we need to use serial transfers, right? So in this case, 2 elements here, 2 elements here, 1 element here, and the overhead that we're going to have here in the execution of our program is that we will have to go one by one, fetching the data or retrieving the data, the output results from the different DPUs. Okay, and how fast are these data transfers? Well, one thing that it's obviously something that you can measure, but one thing that you should take into account is that the maximum transfer bandwidth, it's always going to be bound by the maximum DDR4 bandwidth, because the way that the CPU is connected to the UPMEM DIMMs is through the DDR4 interface. So whatever is the maximum bandwidth that you can achieve, a maximum memory bandwidth that you can achieve in the x86 system is the maximum memory bandwidth that you will be able to achieve when moving data from the main memory to the MRAM. This is not really, or should not really be, a limitation, because when we perform these transfers, what we have to do next is to amortize the cost of these transfers by computing enough on the DPU side, on the pin memory side. And this is something that it's potentially an issue in all accelerators, where you have to explicitly move data, but you normally won't use those accelerators if you are going to just perform a little amount of computation, and usually real world programs will need much more than that. And also one second thing to take into account here is that these UPMEM DIMMs are conventional DIMMs that are similar to conventional DIMMs, and at some point they could directly replace DRAM, and we could maybe even have like only processing in memory capable DRAM in future systems. So in that case, we would completely get rid of this overhead of transferring data from one side to the other side. Okay, one thing that you may be thinking is how is this data moved from the main memory to the MRAM? Because you have already seen the DIMMs, you have seen like multiple chips there, and within each chip we have one or many more banks, and you are already familiar with what's the conventional data mapping onto DDR memory, so DRAM memory. So you know that usually this mapping is horizontal, meaning that consecutive words are in consecutive positions in DRAM rows, and these rows actually span multiple chips. So it might happen that one word or two consecutive words go to, so are mapped on two or more consecutive chips, let's say. And this is something that is not really desirable in the UPMEM pin system, because in each of the chips, we have a processor, and this processor should be able to access the data that is, or is only able to access data that is inside the own DRAM chip, right? So in order to enable that, what the UPMEM runtime system has is something like a transposing library that somehow rearranges in an efficient manner the data and shifts from a horizontal layout to a vertical layout, such as the copy is performed in the appropriate way for the DPUs to be able to access the data they need to operate on. Okay, and after we are done with the data in the MRAM, now we are able to launch the DPU kernel. So what we do is using this API DPU launch, and we are launching whatever we loaded before with the DPU load operation. We launch the computation on this DPU set. And the way that we do this can be in two different ways, can be synchronous or can be asynchronous. In the case of it's synchronous, the application is suspended, the application meaning the application, the code running on the host, on the CPU, suspends until the kernel on the DPU side terminates. Or the other possibility is to use a synchronous launch, which returns, so launches the computation and then returns the control to the application running on the CPU. And at some point, we can check if the kernel completed by using DPU sync or DPU status. We can like enable more functionalities by using this asynchronous execution. Just some examples, for example, potentially it could be possible because the CPU is released, the CPU can do something else, right, after launching the kernel. So one potential thing that we could do here is overlapping data transfers, so moving data from the main memory to maybe another DPU set, while at the same time we are computing on a different DPU set. So this way we would be overlapping these two operations and in summary saving execution time for the overall application. Another thing that we could do here is to enable concurrent heterogeneous computation on the CPU and on the DPUs. Let me give you like a very simple example. Imagine that you have a huge or two huge arrays that you want to add using the vector addition kernel, and what you want to do is, in order to perform as fast as possible, you give most of the input arrays to the DPUs because it's a very powerful setup, but still part of the arrays remain on the CPU side, such that as soon as you launch the vector addition kernel on the DPU side, the CPU can continue the execution here, operating on that piece of the arrays that has been assigned to it, and this way we can accelerate at least a bit the computation. And I'm pretty sure that you can come up with many other examples as well. And the last thing that I would suggest here is that we can use this ability of the asynchronous execution to rank task level parallelism, rank different tasks on different DPU sets, as I also mentioned before. Okay, one last question regarding to the kernel launch is that we typically need to pass some parameters to the kernel, right? And this is something that we can also do with serial and parallel transfers. You have here some example. The only difference is that in these transfers, we are directly copying these input parameters, as well as we can retrieve later some results to or from the WRAM, also called working RAM, which is like a small SRAM memory that the DPUs contain. And we are going to introduce it in the next slides. Okay, maybe some more questions and ideas here. Maybe some of you are asking yourselves what happens with memory coherence or memory over subscription, or in general memory management. How is this handled? Well, at the moment, this is a programmer's responsibility, because you as a programmer will know your application well. You know how to handle data coherence, for example, between the main memory and the MRAM banks, or you will figure out ways of using all the MRAM as much as you can, and at some point move some data, some new data to continue the computation, etc. But at some point, it will be nice to have like some sort of software library that can handle this memory management transparently to programmers. And there is some preliminary work, for example, in the field of GPUs. We have this paper from ASPOS 2010, which was somehow like the seed or the pioneering work for what is called these days the unified memories in heterogeneous systems with GPUs and CPUs, not only for NVIDIA GPUs, but also other vendors, like for example, with the HSA architecture. Okay, now let's take a look at the DRAM processing unit, and let's learn a little bit about how it's built internally, or what are different components. This is the figure from the patent. Remember that we have the SoC connected to multiple DRAM chips, and inside each of these DRAM chips, what we have is the memory array and a processor. So this is actually in more detail of each of these chips. As you can see, there are multiple slices, M slices inside each of the chips, and in each of these slices, we have our memory bank and we have the processor, right, the DPU. Let's take a look at the DPU more in detail, or at this each of these slices more in detail. Recall that this is our current UPMEM system with a number of DIMMs, each of them with a number of pin chips, and each of the pin chips internally look like this. So in particular, we here the current chips, we have 8 of these slices, each of them containing a 64 megabyte DRAM bank and the processor. And as you can see here, the pipeline of the processor is connected to the DRAM bank through a DMA engine. And with this DMA engine, or we can send requests to this DMA engine to move either instructions from the DRAM bank to the instruction memory that we have here, this orange block, or to the working RAM, which is, as I said, is an SRAM memory of size 64 kilobytes. And here is where we are going to have operands and where we are going to store results. So when the execution of the kernel starts, what we will normally do in the very beginning is to send a request to the DMA engine. In particular, the API that we use is called MRAM read. So this DMA engine will access certain data in the MRAM bank and move it to the working RAM. And then once we have the data in the working RAM, we can start running, for example, arithmetic operations in this pipeline. When we compute something, we will write the results back to the WRAM, and at some point we will spill these results from the WRAM to the DRAM bank so that it is accessible through this DDR4 interface by the SoC or the CPU or host. So if we take a closer look at the pipeline, at the moment, I mean, in the next generation, supposedly this pipeline is going to run at 400 megahertz. As you can see, it's a relatively low frequency for the processors that we are used to, but that's what can be achieved internally in DRAM, and in order to achieve this, it's necessary to have like relatively deeply pipeline core. As you can see in the current setup, we are able to achieve up to 267 megahertz. Inside this pipeline, we will have threads running. From the software point of view, we call them tasklets, but in reality, what we have in the pipeline are 24 hardware threads. The in-order core essentially implements fine-grained multi-threading. It's something that you may be familiar with if you are taking the digital design and computer architecture course from Professor Mutlu, or maybe later in this course we will talk about that if we also talk about GPUs as well. So each of these hardware threads has its own program counter, has its own registers, and what we essentially do when we write a program is that we map the software threads, whatever number we are using, onto these hardware threads, and they run in the pipeline. There are 14 pipeline stages. As you can see, some of the stages are divided into 2, 3, 4 stages, yeah, so you can see what's the description of each of the stages here. So for example, the first one is the dispatch, is when we select the next thread that is going to be launched onto the pipeline. Then we fetch the corresponding instruction. Then we read operands from the register file. We format these operands and send them to the ALU in order to perform arithmetic operations, or also to access read or write from this WRAM. And finally, we give the results the corresponding format and move them back to a register. So even though there are 14 pipeline stages, and what we will, the core will be doing is dispatching one instruction from a different thread every cycle. So as you can guess, we are going to have a maximum of 14 threads at the same time inside this pipeline. But from a software perspective, let's say the peak throughput is achieved at 11 tasklets. And this is actually one of the things that we are verifying, because this number, 11 tasklets, is a recommendation from the UPMEM programming guide, and is one of the first things that we have verified with our own experiments. Here you have some results. What we have done here is running some simple micro benchmarks that essentially access the WRAM to read some data, perform some arithmetic operation on that data, and then write it back to the WRAM. In particular, we are evaluating 4 different operations: addition, multiplication, addition, subtraction, multiplication, and division on different data types like integer 32, 64 bits, and also floating point and double precision operands. And the first observation here is that, as we expected, the throughput saturates at 11 tasklets, and this happens for all the different experiments that we have run, no matter what's the data type or what's the operation. One second important observation is that there is a huge throughput difference between addition and subtraction and multiplication and division. You can, for example, observe this figure for integer 32, and we see that it's like, I don't know, so this is around 44 mega operations per second, and here we don't even reach 10 operations per second, mega operations per second. But these results, by the way, are inside a single DPU. So the arithmetic throughput when you have multiple DPUs is like the peak that you could potentially achieve as the result of multiplying these values here to the number of DPUs that you have in the system. So what's the reason for this huge throughput difference between these two types of operations? The main reason is that because of the difficult constraints that the designers had to face because of the DRAM fabrication process, it's not possible to have a 32-bit multiplier inside the DPU pipeline. So the way that they are implementing multiplication and division is not by directly using a native multiplier, which doesn't exist, but it's based on bit shifting and addition. And in total, for this multiplication or division, they need up to 32 instructions that translate to 32 cycles when the pipeline is full, when we have more than 11 tasklets running. There is actually one 8-bit multiplier in the pipeline, but of course you cannot directly use it to operate on 32-bit elements, for example. One idea here would be to explore applications that can really benefit from these 8-bit multipliers such that they can achieve much higher throughput. Yeah, so one interesting research direction here would be to look for these type of applications. Like, for example, reduced precision is used these days in neural network training. So this is probably one potential idea to look at. Second observation is that there is a huge throughput difference between integers and floating point. And the reason is, again, related to the fact that we don't have floating point units in the system, in the pipeline. So it's necessary to also use some software emulation. And as you can guess, it is even more costly than performing multiplication or division. Potential ideas for future research, let's try to find more efficient implementations of these emulation algorithms, maybe try different formats. For example, I don't know if you're familiar with the recent NVIDIA Ampere GPU, which contains these tensor cores that they're especially devised for neural network training. So in there to be able to be more energy efficient and high performance, they are using like a kind of mix or hybrid floating point format that allows you to have like a large enough range of values, but at the same time to operate much faster on the individual operands, right? So maybe these ideas could also constitute a potential research direction here. Okay, let's continue with the programming part, and now with the kernel execution, how these programs that we are going to, these kernels that we are going to write are executed onto the DPUs. And what we have to do now is to take a look at the kernel that we as a programmers would write to perform, in this case, vector operation on the DPUs. Observe that the code is relatively simple. It's essentially C programming. And as you can observe in the very beginning, what we do is identifying what's the tasklet that is going to run this code here. Each of the tasklets is identified by its own ID that we can obtain by using this me API. And then based on the tasklet ID, we will assign to each tasklet a particular piece of data from the corresponding chunk that has been assigned to this DPU in particular. So this is the size of the vector tile in the case of the vector addition operation example that's going to be processed by a DPU. And these are the MRAM addresses for A and B, which are our two vector input vectors. And as you can see, what we do here is that for each of the individual tasklets, we find what's the exact address where the computation will start. Then next thing that we have to do is to allocate WRAM. Recall that whatever we want to compute or to operate on inside the DPU, we will have to move the data from the MRAM to the WRAM. So here we have to explicitly allocate the amount of WRAM that we want to use. Keep one important thing in mind is that all tasklets have access to the same WRAM space. So the amount of space that each of the tasklets can allocate is constrained by the maximum WRAM size that we have. Because this WRAM is shared, it's also possible for different tasklets to access a certain WRAM area that might have been allocated by another tasklet. So next thing, already now inside this for loop, because we may need to perform multiple iterations here, is to move the data from the MRAM to the WRAM using this MRAM read that I mentioned before. In this case, we are moving chunks of block size. This block size must be a multiple of 8, and it's a maximum of 2 kilobytes. Then we compute, perform the vector addition, and then when we have the results, we write them back to the WRAM. So from the WRAM to the MRAM. And here, very simple, the vector addition code, as you can see, is plain C code. We have the corresponding tasklet reading the block size that was just copied to the WRAM, and then going through both input arrays A and B and adding them element by element. Okay, I mentioned before a tasklet is a software abstraction of a software thread. I think there is one question. Okay. Sorry. Okay. So yeah, tasklet is a software abstraction of a hardware thread. Each tasklet, as you have just seen, has access to its own memory space in WRAM. And it's possible, as I mentioned as well, it's possible for a tasklet to access the WRAM space reserved or allocated by a different tasklet, right? For that, you need to somehow share pointers, but it's definitely something doable, and we are going to see example in the next slides. And one important thing in order to be able to do that, to share data in WRAM, is that the threads should have the ability to synchronize. And there are different ways. The UPMEM SDK provide different ways of synchronizing the tasklets. So the first of these is the mutual exclusion, is a way of defining a critical section in the code, which it can only be accessed by one tasklet at the same time. You guys must be familiar with mutexes if you are familiar with parallel programming or p-threads programming, for example. Another possibility is to use handshakes. Is something that in principle is a little bit more lightweight, because here it only involves like a couple of tasklets. One of them waits for the other one to notify that something has happened. And another possibility is to use barriers. So when we use one of these barrier wait, what we are doing is we have all tasklets running. When they reach this barrier, they wait until all other tasklets have reached the barrier, and after that, they continue the execution. This is like a very useful way of synchronizing and making sure that for example, certain data that they all will need to use is already loaded into WRAM, or some intermediate results are already stored in WRAM. And finally, semaphores, which are another way of performing synchronization, access to common resources. Okay, and let's take a look at one example of how to use some of these. In particular, we are going to focus on how to use the barriers. And for that, one really interesting and also useful kernel is a parallel reduction. Parallel reduction is used everywhere, including, for example, sparse and linear algebra algorithms, neural networks, etc. It's essentially what we do in parallel reduction is just computing some value from a lot of input values typically arranged into a vector or an array or a matrix. And the thing that we can compute in the example that we are going to see is going to see the addition. So this is the parallel sum reduction of all these elements, but something we could do as well is a different arithmetic operation, for example, a multiplication, or for example, calculating the maximum or the minimum of all these elements. And at the end, we will have a single value, which is the result that we need for further computation. So in a parallel reduction, what we want to have is multiple DPUs probably, and for sure inside the same DPU, multiple tasklets operating on some input array. What we do is dividing the computation, distributing across the multiple tasklets. For example, tasklet 0 is going to work on these 4 elements here, tasklet 1, tasklet 2, and tasklet 3. In the end, what the tasklet 0 is going to do is adding up the corresponding element A0, A1, A2, and so on to this accumulator that we have here. And the way that we need to do this is by having some sort of intermediate step in which each of the tasklets has like a local sum. So tasklet 0 adds these 4 elements and stores the result in this local sum. Then tasklet 1 does the same for its own local sum, and so on. But at some point, the interesting part here is that we will also have to reduce these 4 values here, right? And there might be different ways of implementing this. And actually, we are going to talk about 2 possibilities here. So the very first thing is to take a look at what each of the individual tasklets does with the corresponding piece of the array that has been assigned to them. So for these 4 elements here, what the tasklet does is reading from the MRAM to the WRAM and then performing the reduction, which essentially means reading one of these elements from the WRAM and accumulating into some local count. And at some point, this for loop will finish because we have gone over all the elements that were assigned to this tasklet. And now what we have is the local sum, and we have to reduce all the local sums, right? So, yeah. So the first, simplest way that we could implement this is by using a single tasklet. Instead of using the 4 tasklets that we had in your figure, let's use just one single tasklet. For example, tasklet with ID equal to 0. And after all other tasklets have finished the computation, we use a barrier in order to make sure that all of them are done with the previous part of the program. They all synchronize here, and right after that, tasklet ID 0 takes over and performs the sequential accumulation by going one by one over the local counts that have been previously stored in a so-called message array, which is also in WRAM. So this tasklet 0 adds all the elements of this message array and stores them in the actual result in some position in memory. And at some point, we will send this back to the CPU. So this is the simplest way of implementing this, but the problem is that we are using a single tasklet, right? A single thread. Why do we want to have up to 24 if we are just using one? So the thing that we can do here is implementing a tree-based reduction, and it's something that is like a very well-known method that allows us to reduce the complexity of this operation, the reduction, from O(n), which is being n, the number of elements that we are reducing, to log n, because we can have multiple threads operating in parallel. So, we will have multiple iterations and a different and a reducing number of threads working in each iteration. So, for example, from the very beginning, we have these 12 elements, and we're going to have half of the threads reducing these 12 elements. So, for example, in the very first iteration, we have thread 0 adding element 0 and element 1, thread 2 adding element 2 and element 3, and then half of the threads retired. And then we have, in this case, thread 0 adding this partial value here and this other partial value or result here, and accumulating it somewhere, and then next iteration, and so on. So something like that we can for sure implement inside the DPU using the tasklets. What we have, it's slightly coded in a slightly different way, as you have just seen in the previous slide, because in the previous slide what we have is even number threads working, but here the threads that are going to work are threads with an ID lower than a certain value, a certain offset that is being double every iteration, and the corresponding tasklet, which is active, which is working, goes to another position of the array, which is at distance offset, and accumulates the value to with its own value, right? So there are several iterations here. After each of the iterations, we need a barrier because we need to make sure that all the active threads have done this addition here, then they synchronize, and then we can start the next iteration, in this case with half of the tasklets from the previous iteration. Okay, and this that was the second example, the parallel reduction, in order to illustrate a little bit how to coordinate different tasklets running on the same DPU. This is just one of the things that we are doing in our characterization study of the DPU of the UPMEM PIM architecture. We are developing micro benchmarks that allow us to understand very fine-grained details of the architecture related to the what's the bandwidth or the latency of access to MRAM, what's the throughput that we can achieve inside the DPU pipelines. And also we are implementing real-world workloads from different fields like dense and sparse linear algebra, databases, graph processing, bioinformatics, etc. Because one thing that we want to do here is to understand very well what are the actual applications, real-world workloads that can benefit from this type of architecture. Because as you can see, this is not just like say, oh, it's memory bound, it's going to work well on the UPMEM architecture. Well, that's something that we will have to evaluate. As you have just seen, there are certain operations that are not so fast as others. So understanding all these little details is very important to make sure that we know what are the limitations of this architecture, and also make sure that we identify what are the points to improve and propose at some point hardware or architecture or software solutions as well to the current challenges. Okay, so if you want to read more, you can have access to the UPMEM SDK documentation. You can even download the SDK and even install it in your system. It comes with a simulator you can start using yourselves if you want to experiment. And one important interesting reference as well is this presentation at Hot Chips 2019 by Fabry Devaux. I would strongly recommend you to watch the video as well. And for sure, if you are interested, please talk to us, contact me or other people in the Safari research group. We can for sure find ways of, answering whatever questions you have, or maybe even if you are interested in doing research using the UPMEM PIM architecture, or do research to come up with software, hardware architecture solutions to improve the current challenges, it will be really very nice to talk with you. And this is again the executive summary. I hope you have enjoyed the presentation and find it interesting. I'm going to check if there are any questions. Yeah, I don't see any questions at the moment in the chat. Seems like my presentation took a little bit longer than 4 p.m. I hope you do not have many other things to do this evening or afternoon. If there are no any other questions, I think that we are done from our side.
Or maybe I have a question. What is the underlying technology of the UPMEM or of this DRAM Because is it 3D stacked memory or?
No, it's conventional DRAM. Conventional DIMMs, DDR4.
Okay.
As you can see in the slide that
yeah.
Professor
Okay,
Model shown.
Okay, that's interesting. And do I have to, or can I use my existing memory controller to talk to UPMEM, or?
Yeah, exactly. That's exactly. That's how it works. So in principle, you could, if you go and buy some of these DIMMs, you could directly plug them into your system. The memory controller, the CPU, the memory controller on the CPU side, the way it accesses the MRAM banks is the way that it accesses these banks as if they were conventional DRAM. Recall from the very beginning that it has to wait for the bank to be available. It's something that we have seen in slide 14. Let me very quickly share my screen again. Not sure if you can see it, but
yeah, I can see it.
Okay, good. So as you see, the SoC can access the MRAM bank as if it was conventional DRAM, and at some point transmit the command to the DRAM processors. The DRAM processors start the execution, and when the execution is completed, then the memory bank is again accessible to the SoC, and it can access it as if it was conventional memory.
Okay. Yeah, I see. All right.
Yeah, thank you for the question. Any other question? Okay, if there are no other questions, I think it's time to wrap up. Thank you very much for your attention in this talk and the 3 amazing previous talks as well. I hope you have a very nice evening and enjoy the weekend. Thank you very much. See you soon.